Hello? Oh, this is Sunday, I guess. Yeah, today it's Sunday. And we are participating in 968 Give 2 round. Let's go. Turtle and good strings. Turtle thinks a string S is a good string if there exists a sequence of strings such that case list 2. S is a concatenation of these strings. And the first character of TI isn't equal to the last character of TJ. Okay, if the last and the first characters of our string are different, then it's easier because we just we just need to check that the characters are different, the last and the first one. Yes? Because if they are different, then we can cut, for example, first character and whatever is the rest. Okay, we need to read the length, we need to read the string. Yeah, here we have a bool. And we need to return that S0 is not equal to S back. Okay. No, no, yes, yes. Good. We need to check C++23, I think. What's wrong? I need to check. Why can't I send like this? What's wrong? What's wrong with it? Okay, it's already great. It's already great. Okay, let's try to send like this. But why didn't it work like with this editor? Okay, now it works. Good. Turtle and Piggy are playing a game on sequence. They're given a sequence A. Turtle goes first. Turtle and Piggy alternate in turns. Okay, Turtle can remove an element which is smaller than its neighbor. And Piggy can remove an element which is greater than its neighbor, greater or equal. Turtle wants to maximize the value of A1. Piggy wants to minimize the value of A1. Well, maybe I don't get something, but I think it's just a median. I think it's just a median. Yeah, because simply Turtle just removes always the maximum. Turtle always removes the maximum, and Piggy always removes the minimum. Yeah, kinda. It's just the median of the array. So we read vi a n a vi a. Okay, let's copy it. So we run nth element. So if n is equal to 2, then Piggy removes, then Turtle moves the first. Turtle removes the maximum and Piggy removes the minimum. Okay. So Turtle can never remove the minimum, actually. What? Wait, what? Turtle cannot remove... Turtle wants to maximize, but Turtle cannot remove the minimum. So it's just minimum or maximum theory, isn't it? No? Why it's 7? Why isn't it 2 or 10? I don't understand the problem. Turtle wants to maximize. No, yeah, I got it right. So we just need nth element. So Turtle wants to maximize. So Turtle wants the bigger element. So here it's like a dot size over 2, right? Right. Okay, let's make it like 7, and we add a test 2, 1, 2, and 3, 1, 2, 3. I see them already, but I still want them. Okay. Oops. Okay, 1, 1. What? Because it should be int. Well, so now we have 1, 2, 2, 1, 2, 2, 7, 2, 2. Yeah, it makes sense. It makes sense. I also want to check this one. Total gives you a string S consisting of lowercase Latin letters. Pair is pleasant if there is an integer k between I and j. And k is not equal to the next one, or to the first, or to the last. What is this problem? Okay, so first of all pairs where Si equals Sj are already pleasant, and we cannot change it. So they are already good. So we want to maximize the number of pleasant pairs in which the first and the last elements are different. Okay. So we want them to be different. Also, we want to find some third we kinda just want it's a strange problem. Do many people solve it? Yeah, many people solve it. My place is tremendous. Yeah, good. Okay, so or it's or here. It's or here. Okay. So Si equals Sj are already good, so we ignore them. So otherwise, we want to maximize the number of pleasant pairs with different elements Si and hence J. However, since Si and Sj are different, Sk is not equal to Si. Okay, so what do we have? So we have two different elements here, for example, A and B. We want somewhere two different elements such that it is not equal to this one and it is not equal to this one. Okay, assume that there is at least one. So it can look like this, A, and then a lot of B's. In this case, the only pair of different elements is this one, and unfortunately this is equal to this, and this is equal to this. This is bad. What else can we have here? We can have here any letter C which is not equal to A and B, and in this case it is automatically working. Or this pair. So also if we have B and then we have A, this also works because we can take this pair and these are different. Okay. So the only way it can not work is that if we have all A's and then all B's. So we want to avoid that. We would like to avoid that. We cannot always avoid that though, because, for example, if we just have some letter A and then some letter B, they are always not a pleasant pair. So therefore, we kinda want to... So two neighboring elements are always bad, but otherwise we would like to have as many pairs as possible. For example, we can just put all A's on odd positions and then all B's on even positions, something like this. But this does not always work as well. Yeah, it does not always work as well because of what? Because there can be more than half of A's. And what then do we do if there is more than half A's? Well, I don't know. What do we do? What's happening with this problem? Okay, let's try to do something. So we read a string. Okay, let's think. What do we do here? So we have lowercase Latin letters. So let's like okay. We have counted everything. Then what? Okay, first case is that we have so that each character is at most. So let's find the most visited character. How it's done. So we can just say int maximum character is max element of whole c minus c dot begin. So if CMC is at least, let's also say we have size of S. If we have n plus 1 over 2, at least, at most, then it's kind of easy. So we fill S with these characters. Okay. Okay, what I want is I want a string t and um, the order of indices. And in the end, I will say string ans, and for int I from indices, ans plus equals ti. This is what I want. I want to prepare t and indices. Let's prepare them. So if this is true, then t is first of all CMC of a plus MC, and then if I is not equal to MC, t plus equals string of CI and a plus I. Otherwise, also I want indices. Indices are just first of all odd indices, then all even indices, right? Right. Okay, otherwise, we have a very popular element. And since we have a very popular element, we kind of do the same, but start with the odd ones, I think. Okay, so I think this is common. But indices are done like this. I don't know. There's something I really dislike about it. Actually, I think we always want it like this. Yeah, we always want it like this. We only want one block of A's. We only want one block of A's. I think I messed up. So again, actually I messed up, yes. So we have, or I did not. What's wrong with my tablet? It randomly shuts down. So we have a string. Again, how many bad pairs? So for each block, C, 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 D, 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 how many bad pairs? So each pair like this is a bad pair. So in my case, how many bad pairs do I have? I have, so I put A's like this. And then I put everything else like this. And I have something here. So how many bad pairs do I have? I have bad pairs. The number of bad pairs is equal to the number of of A's. So for each A, there is one block like this, but also there are like CA and then AC. Okay, what I want is that I want, starting with each character, at most one bad string. It is always possible. I want at most one bad string starting with each character. Yes. And it's always possible, so it will be n minus 1. And here, yes. So basically, I really, in any case, I can start a bad string with any character except the block of equal characters in the end. However, if I have a block of equal characters at the end, then I have more than one string starting here. Because I said there is only one string, but I can also make these strings. And since I can, there always will be at least n minus 1. So that's what I want. Yeah, I just always want these indices. It's a mess of a problem, but okay. Why is it like this? Is it okay? Is this okay? Why did it happen? Why T is... what? What's happening? Why is it like this? Why C? Ah, okay. I need to say n's indices I equals ti. Okay, I think it's fine. Good. Or not, I don't know. Problem with G1. Turtle was playing with n sequences. The length of the ith sequence is li. Yes. Then we get another problem. There is a non-negative integer x. We perform an arbitrary number of operations on this integer. And we can several times set x to max of x and a sequence. Okay, this is an easy problem because we can either set an integer to the max of these numbers and then try again and set it to the max of numbers with x. So like for any sequence there is max and second max, and we just choose the maximum second max, I think. Pika gave Turtle a non-negative integer m and asked Turtle to find the value of sum of fi's for all i's. Okay, it's simply maximum of initial number or second max of the sequence. Right? Okay. How do we find the second max? So second max is at most n plus 1. It is at most n plus 1. No, it is at most n. Ah, yeah, it is most n plus 1. So, int I from a. What is max? Max is smallest non-negative integer, yeah. So we say that if I is less than v dot size, vi is false. And then we want to find the second true in this array. So if vi plus plus c, and if c equals 2, return I. And here, for example, return anything. So we can now find second max. So first of all, I want to find the maximum second max. Secondly, I want to find the sum. So if second max is actually here we have m. If second max is at least m, then it's easy because we just find the sum of all numbers from 0 to sm to m. No, we just return Um, m times what? Ah, m plus 1 times sm. Otherwise, we take sm times sm plus 1 and plus sum of all numbers from sm plus 1 to m. How do we find this sum? M plus sm plus 1 times m minus sm over 2. Good. So here we need to read n and m. Then we need to read n lines. Where we read the length and then the sequence. Yes? Then we print this and this. Okay. 1620 1281. 665 567 85365. Yes. Oh, yeah, you should solve it 7 minutes, not in 29 minutes. But what can you do sometimes? Okay, this time it's the same, but we cannot choose the same sequence twice. So now it's kind of harder. Oh, no. Okay, how is it harder now? Okay, now what? I cannot do it. What's wrong with you? Okay. So this time, okay, this time we have again, for each sequence, we're only interested in its max and second max. We can call them A and B. So we have several pairs A, B. A1, B1, A2, B2, etc. AK, BK. We have some starting number. So what can we do? We can, for each sequence, we can either set this number to the first one, or if it is already equal to the first one, we can set it to the second one. And we want to maximize it. Yeah? So first of all, it never makes sense to reduce the number unless it's the first operation. Yeah, we can reduce the number if it's the first operation, but other than that, it does not make sense. Why? Also, it does not make sense at all to run more than one of such operations. Yeah, because if you invoked A1 and then you invoked like A6, you can, from the beginning, invoke A6. And if it is already equal to 6, you can just not invoke anything at all. So you can perform only one such operation. Okay, you invoked one such operation. Note that you also don't want to invoke two operations of this kind. You can want. Maybe you sometimes want to invoke several such operations. Okay, M. You invoke at most one of such operations. And then you can invoke a series of these operations. So let's draw it as a graph. So as a graph, we have some number M, and we have some ordered graph, like this, like this. Okay. So first of all, let's find the maximum answer if M is equal to 0. So if M is equal to 0, what's the maximum answer? Maximum answer is what? So first of all, we can always take the maximum of these numbers. It's always possible. Secondly, what? Secondly, if there is a number which appears twice on the left side, if there is a number which appears twice on the left side, we can jump in it and we can go to the right as far as we want. Also, these numbers are not very big because otherwise, well, they're not very big. We can use that. Like their maximum is small. Their maximum is very small. And we can work in O of the maximum of these numbers. Actually, the sum of b's is also very small. The sum of b's is really, really small. Yeah, the sum of b's is small because each b, to be established, you need to put all numbers less than it except 1. So the sum of b's is really small. Yeah. Okay, so for each number, we want to find the maximum which we can reach from this number going forward. Then we want to find the M0 answer. M0 answer is the maximum among all numbers which appear twice as AIs. Or simply just AIs. Then for each number A, we change that answer. Okay, it makes sense. Okay, let's find max and second max. PII answer plus plus C, so if C equals 1, then answer dot X is I. If C equals 2, then ans dot Y equals I. And return answer. Good. We can find second max now. So we now go. We find all maxes. Okay. What now? Okay, now we have three types of numbers. Yeah, from 0 to M. We have three types of numbers. We have some AIs. We have some AIs. What else do we have? So we also have numbers which are less than M0. And we have numbers which are greater than M0. Okay. Okay, let's go. We need like an ordered map from int to multiset of ints u. And now we go through all pairs. I can do it here. Okay, now we say that u p.x dot insert p.y. Okay, this is a base. Now I want to find the jump array. So for each integer I from here, actually I want a map here again. From each number from here, I want to find the maximum jump that I can make. Okay, let's go. So for auto it equals u.r begin, it u.r end plus plus it. So I take it, and it is an edge from some number to some number. Also, I want m0 and int m0 equals 0. So first of all, m0 is maximum of m0 and itx. This is good, okay. Secondly, I want to find some jump from j. Let me think. So I say that j itx. I want to find j itx. So int like y is ity. Int y, okay, equals itx. Then I want to iterate through all y's. Then so if u contains 2, then y is maximum of y. Okay, if j contains 2, I think. Maximum of y and j2. Else y is maximum of y and simply 2. And then I say here that it is equal to y. Okay. Also, if ity dot size is at least 2, then m0 can be updated with y. Else m0 can be updated with itx. Okay, now I know m0 and I know the jump place for all numbers. Okay, so let it be m0. So I have two types of numbers. I have numbers which are at most m0, and I have numbers which are greater than m0. Yeah, I have numbers which are greater than m0 and at most m0. Two types of numbers. So for all these numbers, the answer is simply m0. For all these numbers, the answer is simply I. However, each time that I need a I for some... Okay. Let's say that I have answer which is what? Which is... So for all these numbers, I have simply m0. So how many numbers do I have? I have minimum of m and m0 plus 1 times m0. This is my left answer. The right answer is sum of all numbers from m0 plus 1 to a minimum of m and m0. So how can I calculate it? So first of all, I kind of want to find this number. Let it be a m, capital M. So I say here that I want to find the sum of all numbers from m0 plus 1 to capital M. And as I said, it is m plus 1 times m minus capital M over 2. Okay, this is my basic answer. Now I again need to go through the array J. So if p.x is greater than m, then I continue. I'm not interested in this number because it does not affect the answer. Okay, if p.x is at most m0, then it's here. So I need to subtract m0 and add the actual answer, which is j, which is py. So, and py is greater than m0, then answer plus equals py minus m0. If px is greater than m0, but yeah, and py is greater than px, then answer plus equals py minus px. And then I return answer. Okay, there is some gargantuan example. Let's see what it says. 16, 18, 20, 81, 4, 65, 65. Yes, probably it's okay. Is it really a two-hour contest? And I already struggle with D2. Wow. Oh no, it's fine. It's fine. Okay, problem E1. Again, two versions. Total gives you m intervals. He thinks that a permutation P is interesting if there exists an integer ki for every interval. So he can divide each interval into two parts, such that the maximum in the left part is less than minimum in the right part. Okay, it makes sense. Total wants you to calculate the maximum number of inversions of all interesting permutations of length n. Or tell him there is no interesting permutation. Okay, first things first. In this case, all intervals consists of at least two numbers. So if we just take the increasing permutation from 1 to n, then it is always interesting. Because you can divide wherever you want. For example, L at the point Li. And the left maximum is simply Li, and the right minimum is Li plus 1. Very simple. Maximum of all A's is less than minimum of all B's. What? What? Still, we can always put some small numbers on AIs and some big numbers on BIs. Okay, makes sense, makes sense. makes sense. Okay, what do I think about it? I think about it that so first of all, we have several segments. Let's first assume that they're non-intersecting, but never mind, they can even intersect. What about these places? So here we have some empty places. Of course, for example, here I think we want n because it maximizes the number of inversions. And here we want n minus 1, etc. But what about this place? What do we want there? What do we want there? It's not so obvious. For example, if the maximum of all black numbers is here, we definitely want to put here just the maximum of all numbers. We want to maximize the number of inversions. And in E2, what do we want? It's guaranteed that the sum of n over all test cases does not exceed 5,000. Some dynamic programming, isn't it? Okay, so we have several segments. We have several segments. They do not intersect. Right? So what can I say? I can say that this number okay, first of all, in the best case scenario, we would like to have here like k, k minus 1, k minus 2, etc., k minus something. Instead of that, we cannot have it. We need to have some subdivision point where all these numbers are smaller than all these numbers. So we will lose LR inversions. And if we will have to lose them, the best thing we can do is divide here. So we lose the minimum number of them. So we always put here like minimum of this segment, and here we put them in decreasing order. And if we do it along this array, this will optimize this function. Okay, it's easier. Let's try to do it. So we read n. We need to read n and the number of segments. Length of the permutation, the number of intervals. VPII segments of size m. We read, okay, like we read SI. We read SI and what? I think we want to subtract SI.x. So we have all intervals. Then we need to output what? output the number of inversions. So we need to put here n and s. Okay. So basic answer is simply this. However, for each segment, we lose the number of inversions equal to the length minus 1. Just the length, I think. For example, 2 numbers, then I lose 1 inversion. Okay, that's it. Is it a very easy problem? Much easier than D, I think, even. Minus 1? No, no way. Why minus 1? Ah, as I said, minus 1 here. 1, 0, 8, 20. What? Here, 1, 4, and 6, 8. So on 8 elements, right? On 8 elements, there are 35 inversion. What? Ah, maximum of of AI. Again, I have a blackout for some reason. Let's see what's happening. Actually, we have several segments, and all these maxima should be less than all these minima. All. Okay, let's subdivide each segment. Yeah, all these maxima. All these numbers should be less than all these numbers. Do we again want to move this red line to the as left position as we can? Okay, first of all, let's consider the case, for example, when we have two segments which cover the whole array. What do we do here? So we want all black numbers to be less than all green numbers. So definitely black numbers are simply like 1 and 2, and green numbers are simply the rest. Then first, Now it depends. It depends on the position, doesn't it? For example, because the other thing that we could do is we could cut it here and take here to maxima. Let's compare. So for example, we have segment from 1 to m, and here from m plus 1 to n. Yeah, so there are two things basically that we could do. We could cut here and here, put here 2 and 1, and put here all numbers from n to 3. How many inversions are there? Okay, how many non-inversions are there? Non-inversions are 2 and everything. Like 2 and what? 2 and everything except 1 and 2. So n minus 2 non-inversions. And with this number 1, there are all inversions with these n minus m minus 1 numbers. In total to n minus m minus 3. Okay, good. The other thing is when these two segments and we cut them here and here. So here we put n, here we put n minus 1, and then n minus 2 and minus 3, etc. etc. 1. So how many non-inversions are there here? So n has a bad pair with each of these numbers. We have here m. So we have m minus 1 non-inversions. And also n minus 1 has a non-inversion with n minus 2 numbers. Okay, so we can have n plus m minus 3 or 2n minus m minus 3. Well, yes, it depends on where this m is. Can we have less in non-inversions? I guess no, but I'm too lazy to prove it. I don't know. The only thing that comes into my mind is that we can try only cutting the left element or cutting only the right element. Maybe it works. I don't know. Okay, let's assume that we cut only the left element. We cut only the left element in our assumption. So we have several segments. In each of these segments, we have this left element. And these should be greater than everything here. They should be smaller than everything here, right? Yeah, all of these numbers should be smaller than everything here. So if we do not have anything here, so nothing here, nothing here, nothing here, then we just put, so for example, m segments, then m minus 1, etc. 1. And here we put all maximum numbers in decreasing order. Great. Now for each position here, 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 we want to choose the best number that can fit there. And how can we do that? For example, here. How can we fit the best number here? Well, by iteration, I think. Or how? I think it just should be between this and this. It's the only thing that makes sense. Okay, so in this case, how many inversions do we lose? For each this number, we lose all inversions of m with everything except black. Okay, how many non-inversions are there? There are this number of non-inversions plus this number of non-inversions plus this number of non-inversions. No, it's wrong. It's wrong. It's wrong because I think, for example, if I have segment of length 2, yeah, then I want to put here 1, and then I will put here n minus 1, n minus 2, etc. Then something here, then something here. And this is bad because instead of that, I could put here some bigger number. Okay. I think I realized it. So yeah, so there are two types of numbers. So let's find, so let's call these numbers orange. These numbers are orange or yellow, I don't know, orange number, honey numbers. So let's find the median honey number. It seems that all numbers here should be greater than the median honey number. They should be just the greatest possible numbers. And all numbers to the right of the median honey number should be less. It still looks like a pretty damn bad thing. I only need to find the number of inversions, yes? Okay. So I find the median honey number. I find the median honey number. So then everything here just gets n, n-1, n-2, etc. No, it's very bad. I don't get it. I don't get it. Okay, maybe I just don't like this problem. I don't understand it. I really maybe I'm sick a bit, but I just cannot comprehend it. Let's look at problem F. Piki gives turtle three sequences A, B, and C. Turtle will choose a subsequence of 1 to n of length m. Let it be P's. The subsequence should satisfy the following conditions. A is on these positions are non-decreasing. B's on these positions are pairwise different. And we need to find the maximum value of sum of C's. What are these problems? Ah, M is at most 5. Ah. Okay, if M is at most 2, it's easy, because we can just iterate over all possible subsequences of length 2. Okay, if we have length 3... Okay, let's for now forget about B's. So B's are pairwise distinct initially. In this case, it is a dynamic programming. Yeah, for each index, we want to find the longest. For each index and each length, we want to find the maximum value of this thing, ending in this index. Okay, kinda easy. What about equal B's? With equal B's, it's worse. But still not that bad. Right? Because, you know, okay, we have 5 indices, right? So we take the first one. Okay, let's look at it somehow. So we have some A's. We have some number here. So B's should be pairwise different. So therefore, we cannot have this number. So we would like to have some subsequence before that, but we cannot because among these B's there is already this number, right? Okay, I think the least disgusting implementation would be with some memoization. So we write a function f which says find some sequence of length L ending with AI with only different B's, with only different BIs, distinct, and that does not have the following set of forbidden BIs. And the set of forbidden BIs will always be at most like 4. Does it feel right? It does not really feel right, but let's just try to do it. It might work, I don't know. So we have N and M. We have ABC. And we need to print the maximum value of this function. Okay, so what do we do in our memoization? In our memoization, for each index AI and for length L, we have several answers. We have several answers. So we iterate over them and check if there is some forbidden BI. If there is not, then we take the biggest one. We just take the biggest one. Okay? What? No, I don't like it. I don't like it. Okay, if there is some answer whose forbidden BIs are subset of our forbidden BIs, and they do not contain these forbidden BIs, we win. Otherwise, we need to run a new memoization thing. Okay, let's do it. So how do we do it? We have vector by length, then vector by index, and then just vector of pair of something. Length will be at most m+1. Okay, pair of what? Pair of forbidden BIs? Pair of forbidden BIs and the answer. And the answer can be vector of indices, I think. Okay, let's make a tuple of vector of forbidden BIs, a vector of chosen indices, and their sum. Okay, this time it is for each index, where we end. Okay, n+1. Okay, n. Then we just have an empty thing. Okay, memoization. Okay, good. Let's now write function auto or not auto. Find answer with memo. So we have our memoization thing. Okay, first of all this. Then we have length, index, and memoization. Array. So what do we do here? We also need the vector of forbidden bees. Okay. First of all, we need to check something trivial. So if L equals 0, then it's easy. We just return 0. Okay, if L equals 0, then return 0. Okay, what next? So if index is less than L, this means that it is... we want to end with index. So if it's less than index minus L minus 1, then it's really bad. L minus 1. Okay, also I think if in this position index if B index is in this set forbidden, let's say that it is set in. If forbidden contains this, then also return -1. We can't help but lose here. Okay, good. Now, -19 minutes on this awful problem. Okay, now this time forbidden does not contain B index. Also, I want to check if our answer lies in Mimo. Yeah, so how do we check that it is in Mimo? Okay, let's make set int for now forbidden, which is initially empty, right? Okay, while okay, what do I want to say? I want to say that I want in Mimo, in L index, find my answer. Okay, let's take it. So there are some tuples. Forbidden bees. What is the answer and what is the answer? Okay, let's go through it. Forbidden. Answer indices and answer just answer. Okay, let's look at it. So if our set is a superset, okay, if it equals, so if for now forbidden equals does not equal form, then continue. Okay, while true. Let's do it while true. So we go through this array. Bool found something. Okay, if we found something, then we say here true. What then? Then we need to check if there are no forbidden items here. How do we do that? We go through ans I, and if bi is contained in forbidden set, bool unfortunate. And then we have to add it here and say that unfortunate is true. Right. Okay, if we found something, if we do not find something, we need to store the new memoization result. Okay, so here, if okay, what else do we need to do here? Also, we need to say that if answer is -1, then we ourselves have to return -1. Yes, so we say that memo L index okay, we found our situation. We found our situation in memo. Then we just return -1. We can do it here, I think, immediately. So we found something. Okay, if we did not find anything, we need to firstly store the answer. Okay, if found something, but if not unfortunate. Okay, I think if not unfortunate, then we won, right? We won because we found the correct answer. We just can return answer. 9 minutes? Yeah, 11 minutes. So now we have found something, but it is unfortunate. There are two cases. Either we found something, but it did not fit, and then we need to repeat because we have a bigger set for now forbidden. So if found something and unfortunate, then we need to continue. Okay, the second case is that we did not find anything. So if for now forbidden does not equal to forbidden, then we also have to repeat. We also have to repeat. So A, B, C, L index. But now, instead of forbidden, we have for now forbidden. Because it is smaller. And Mimo. And also continue. Okay, now the only case is that we found something, but it's still, we did not find anything, but we need to forbid everything. So we say break. Okay, what then? Then, in this unfortunate case, we need to calculate our answer ourselves. And we need to iterate over the previous index. Okay, we also have a VI answer indices and int best answer, which is -1. Okay, what do we do here? Actually, I want a pair of VI and int. Good. So we run this function with ABC L-1 ref index forbidden and Mimo. If we have found it, good. So if ref answer is less than 0, then continue. We also need to forbid our current index. So for now forbidden, we can put here B index. Okay, if prevents is less than 0, then continue. Otherwise, what do we say? We say that ref ans plus equals C index. And if also, yeah, so if a ref index is greater than a index, then also continue. Yeah, it's the most important thing. We added C, so, and if ref ans is now greater than best ans, then ans indices equals ref indices, ans indices push back index, and best ans equals pref ans. And here we simply return best in ans synthesis and best ans. And here, actually int instead of ll, it will be fine. Here we return find ans with memo of abc m find ans with memo of this, and finally forbidden add memo. And here I need to take dot x, dot y. Okay, of course it's not good. I also need to store the answer. I need to store the answer. So I need to say that memo l index and place back what? So forbidden and these two. What's wrong? I need to put here vi. -1. Excellent answer. Does it give an answer at least for anything? For something? Okay, for it gave 13. So we only needed to give 5 here, and it will be great. What? I need to return the answer if index equals 1. Okay, if L equals 1, we need to return forbidden index and a index. Okay, but I have run out of time, unfortunately. But something like this should have been written here. And also I need to store it in Memo, I think. Okay, Memo. Okay, I don't want to store it in Memo, actually. So basically, yeah, basically I don't want to store it in Memo. Okay, now it says 6. It says 6 because it took 3 and 4. Okay, let's fix that. Okay, now the best answer is 4. 4? How is it 4? What is C2? 2? What are you talking about? One zero and it says the answer is 2? How does it do it? It's C index. Right. Okay, now it gives some answer. Now it gives some answer, but I cannot submit it. Wow. Why don't they fix it so I could submit it before the end of the contest? Like after the end of the contest. Okay, let's discuss the problems. And most probably I will resubmit it after the system testing after this video ends. Okay, problem A. Turtle thinks a string S is a good string if there exists a sequence of strings of length at least 2, such that S is their concatenation, and the first character of each string isn't equal to the last character of any subsequent string. Okay? So I claim that answer is yes, if and only if A0 is not AN-1. So let's prove it in both directions. Assume that the answer is yes. So there is a division into several strings such that in each string the character, the last character, or the first character is not equal to the last characters of any subsequent strings. So all yellow lines connect to different characters. Okay, these ones also, these ones are different, and these ones are different. Notice that among these lines, there is this line, which connects the last character of the string and the first character of the string. They are always should be different since k is at least 2. Since k is at least 2, this string and this string are different ones. And the first character of this string should be distinct from this one. Therefore, we get this inequality. Now let's draw this arrow, and this is also very easy. To do that, let's just assume that there are two different characters A and B here. So then I claim that this division is correct, because all we need is that k is at least 2, which it is, and this character should be different from this character, and this is also true because of this inequality. Therefore, to check the answer, you just need to compare the first and the last character of the string. Problem B. Turtle and Piggy are playing a game. So they're playing a game. In this game, Turtle basically takes two neighboring elements and removes the smaller one. And Piggy takes two adjacent elements and removes the bigger one. Right? So Turtle wants to maximize by removing the smaller element. And Piggy wants to minimize by removing the bigger element. What is the number that will be after the optimal play of both players? So I claim that it will be the median of the array. In our case, upper median of the array. So in case of an even array, yeah, let's sort it. So I with parentheses is the sorted array AI. So I claim that the answer is A n over 2 plus 1. So if there are like 4 elements, then we need this one. And if there are 5 elements, then it's also the third one, right? So we need the median. How can we define the median in another way? Another way, median is the only number x such that in the array there are at least, let me think. In this array, yeah, there are at least y over 2. Or no, not y over 2. Okay, what is the median? So basically, okay, if we have an odd size array, like n from 1 to n, where n is odd, what is the median? Median is the number such that there are at least n plus 1 over 2 elements which are at least x. And there are at least n plus 1 over 2 elements which are at most x. Okay? In the case of even size array, we take the upper median, which is a little bit bigger. And since it is a little bit bigger, we need to change these two numbers. So we need at least n plus 2 over 2 elements, which are at least x, and at least n over 2 elements, which are at most x. Okay? In case of both parities, we can write the uniform formula, which looks like this. So the number of elements which are at least x should be at least, well, n over 2 plus 1. It should always be at least n over 2 plus 1. Yeah, and the number of elements which are at most x should be at least n plus 1 over 2. So this is what I claim. So I claim that there is exactly one number x for which these two inequalities hold. Moreover, this is the median, which will be the answer. Now I will give to you two strategies. Strategies for the first player and for the second player. Let me remind you that the first player wants to maximize the number. So, theorem. First player can guarantee that the answer is at least x. Okay? What will be his strategy? Strategy: always remove the minimum. Okay? The key observation why that is the case is that we need to look at the numbers which are smaller than x. Oh, no, numbers which are at least x. Okay, let's look at the numbers which are at least x. So the first case is that at some point all numbers are at least x. If that is the case, then the last number will also be at least x, because if now all numbers are at least x, then inevitably the last will also be at most x, because the number which is less than x cannot appear in any way. So this is automatic win. The second case is that not all numbers at least x at any moment of the game. We will prove that it is actually impossible. In the end, there will be only one number and it will be at least x. Why? So let's assume that not all numbers at each moment are at least x. Let's see what our strategy does. It always removes the minimum. Obviously, minimum is less than x. Yeah, since not all numbers are at least x, then minimum is definitely less than x. This means that the following is true. First player never removes a number which is less than x. He never removes such a number. Which is never removes number which is at least x. The only person who can remove a number which is at least x is the second player. The first player, by our strategy, never does it. Notice that he can remove the minimum because the minimum is always adjacent to some bigger number, so we can remove the minimum. Bigger or equal number. So the first player can, by the strategy, never remove such a number. So only second player can remove it. AI, which is at least x. So how many moves does the second player do? Second player will take n minus 1 over 2 turns. It's easy to calculate. In the beginning, as we know, the number of numbers which are at least x is at least n over 2 plus 1. Let me write it. So initially, n over 2 plus 1 numbers. Second player takes this number of turns, so he will remove at most this number of numbers. And this is at most this. So it will, in the end, it will be at least 1. Right? So always, I don't like actually something. Yeah, because it is because it's strange. Sorry. The numbers which are at least x, it's vice versa. So in the case, it's vice versa. Sorry. The numbers which are at least x, there are n over 2 of them. And the numbers which are at most x, there are n plus 2 over 2. So actually, these formulae look otherwise. So this is n plus 1 over 2. And this is n over 2 plus 1. Okay, so if we look at the numbers which are at least x, then initially there are n plus 1 over 2 of them. So in the end, there will be at least n plus 1 over 2 minus n minus 1 over 2, which is simply 1. Numbers which are at least x. Or at some moment, all numbers will be at least x, which means that the last one will also be at least x. So therefore, by this strategy, the first player can guarantee that the last number will be at least x. Okay, now let's look at the second player. let's prove that the second player can guarantee that answer will be at most x. She will basically do the same. So the strategy: always remove the maximum. She can, because the maximum is adjacent to some smaller or equal value, so she can do it. And again, there are two cases. First of all, if at some moment all numbers are at most x, then win, because the last number will also be at most x. Secondly, never all numbers are at most x. This means that she can always remove the maximum, and she never removes a number which is at most x. So only the first player can remove such numbers, right? So notice that the first player takes how many turns? The turns n over 2. So initially, there are n so initially there are n over 2 plus 1 numbers which are at most x. So in the end, at least n over 2 plus 1 minus the number of turns taken by the first player. This is again 1. So in the end, there will be one number which is at least x, at most x. So the first player can guarantee that the last number will be at least x, and the second can guarantee that it will be at most x. Therefore, if they take optimal turns, it will be exactly x in the end. So you just need to find the median of the array. Okay, good. Problem C, turtle and good pairs. So we have a string s. Actually, I think, did people really like this round? I did not, actually. Unfortunately for CLT, the round was like, I don't know what to say about it. I wouldn't say that it's just guesswork, but well, okay. Problem C. We want to reorder our string so that we can maximize the number of good pairs. A good pair is a pair where si equals sj, or if there is an index between I and j such that the symbol is not equal to the next one, and either of these two things is true. So first of all, we need to understand what is a bad pair. Bad pair is not a good pair, but still I is less than j. So how can a pair be bad in our string? First of all, these two symbols should be different, these two characters. because if they're equal, then it is a good pair by definition. Also, there cannot be any index which is at least I but less than j, such that these two characters are different, and these two different, or these two different. Okay, let's find such an index where this holds. Starting with A, let's go A, until we find some other character. Okay, if it is not B, for example C, then these two characters are different, and while these two are same, these two are different, right? So if we at some moment find any character which is not equal to B, then we win after A's. So the only problem is that we have B here. Okay, let's continue and see B, 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 B. If at some moment we also find some character which is not B, it can even be A, doesn't matter, then these two characters are different, and these two characters are different, and we immediately win. So the only way it can be a bad pair if these B's continue till this position. So bad pair is actually the number of substrings of form a lot of some characters and then a lot of some other characters. We want to avoid that. Well, I claim that you can get as many as only n-1 bad pairs. In any string, you can get only n-1 pairs if you want. And if all characters in the string are same, like here, then there will be no bad pairs at all. So I claim that if in the string there are at least two different characters, then the minimum possible number of bad pairs is n-1. Then if you want to calculate the number of good pairs, you will have to calculate n times n-1 over 2 minus n-1, which will be n-2 times n-1 over 2. Good. Let's find the number of bad pairs. Firstly, I claim that it is at least n-1. Let's take our string. Starting with each character, I will provide you with a bad pair. How will I do it? I will take this character, then I will wait until it changes, and I say that this is a bad pair. Okay, for example, here we have B. Again, starting with this character, I go until I find some other character, and I say that this is a bad pair. Starting with each index, I will find you a bad pair. Except what? Except this last block. So if I have the last block of equal characters, then starting here, I did not find any number of bad pairs. For now, how many bad pairs I have found? I have found n minus b bad pairs, where b is the length of this block. So now I only need to provide you with b minus 1 more blocks. That's what I need to do. Let's take the previous symbol. The only bad pair starting with this symbol that I found was this one. Well, I can easily find b minus 1 more pairs. This, and this. So these are b minus 1 more pairs, and if I add here b minus 1, I get n minus 1. So in any way, if you reorder this string, you get at least in any way, if you reorder your string, you get at least n-1 pairs. Now I need to provide you with the way where it is exactly n-1 pairs. Okay. What will be this way? This way will be the following. Firstly, there are several possibly equal characters, and then there is a string where each pair of adjacent characters is different. So firstly, you have a block of equal characters, maybe of length 1, and then all adjacent pairs should be different. If you do it, you win. Why? Let's consider any block. Let's consider any bad pair. Let's consider any bad pair. So there are two types of bad pairs, which contain one of these characters or which don't. So if a bad pair does not contain this A, then it can only be something from here. Okay? It can be nothing except these ones. Because if you take at least 3 characters, then it's not like a block of equal and then again a block of equal. So if there are B A's in the beginning, then we found how many pairs? N minus 1 minus B, right? Okay, and also how many pairs in which there is at least one A? So it starts with an A, obviously, and it can only end with this B. So for each element of this block, there is exactly one pair. So we get plus B equals n-1. So the only question is how to reorder our string such that it starts with several A's, with several equal characters, and then it does not have any two adjacent equal characters. I claim that in order to do that, you need to... So first of all, let's sort our string. So all A's in the beginning, then all B's in the beginning, then all C's in the beginning, D's and E's, etc. What I would like to see here is that this block should be the longest among them. So let's assume that A is the most popular character in the string. If it is not, what do we need to do? We need to not really sort the string. We need to sort it that way that firstly we have a block, the longest block of equal characters, and then we have all the other blocks. But this is what I want. So I want to reorder the characters such that they are in blocks of equal characters. Yeah, each character is in its own unique block of equal characters. And the first block is the longest one. Okay, this is what I want. Okay, this is the string t. So t0, t1, t2, etc. Tn-1. This is a sorted string. And now I will construct the string that I really want. How it looks like. Answer. So here we have t0, then we have t1, then we have t2, then we have t3, etc. Then we have t... n minus 1 over 2. Then we have tn plus 1 over 2, tn plus 3 over 2, and we continue on the odd positions. So we started with even positions and then go with odd positions and continue putting these symbols. So I claim that this is a string of this kind. So it has a block of equal characters and then no two adjacent characters are equal. Let's assume their complement. Let's assume that here we have two equal characters. Okay? So what do we see? We see that ti is equal to some character, for example x, and then t, either this one or this one, is equal to x as well. Okay, for example, right one. What if the right one is equal to x? The right one is I plus n plus 1 over 2. Oh, minus. Plus 1 over 2, yeah. It is equal to x. Therefore, I have all characters from I to I plus n plus 1 over 2 equal to x. Therefore, there are at least n plus 3 over 2 equal characters. In the second case, when this element is x, I will have I plus n minus 1 over 2, and this would mean that n plus 1 over 2 equal characters in the row. Let's take the least one. Still, this is obviously the most popular character in the string. This is the most popular character of the string. So there are two cases. Either it is just t0, or we have two characters which are equally frequent. So the first case, two characters. There are two different characters which appear at least n plus 1 over 2 times. Then in total, they appear 2 times n plus 1 over 2, which is at least n. It is immediately at least n, and the only way it can be exactly n is that n is 2k, and we have k characters like a and k characters b. So there are two most popular characters, they're equally popular, and there are no any other characters. In this case, our string will be a, and then b, 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 b. So obviously there are no two equal characters in a row, and that means that it is a good string. It's fine. Second case, there is only one character which is at least this popular. That means that this character is t0. That means that actually what was happening is that we put all put the most popular character A all among the string, then we continued here, filled something, and then stopped and filled these places with something else. But this exactly means that we have a block of equal characters, and starting with some point, all characters were different, adjacent. Therefore, this also works. So, indeed, if we sort all characters in a way that we start with the most popular block and then something else, and then we reorder them according to the parity, then we get this type of string. This type of string. So, several equal characters and then all pairs are different. This is what we wanted. Okay. Problem D. Turtle and the max problem. We have several sequences. We have also a number. We can replace a number with max of it and the sequence several times. We want to maximize the number x, and we want to find the sum of all numbers fi from 0 to m, where fi is the maximum that can be achieved starting with I. Okay? And there are two versions. In the first of them, we can choose the same integer twice or more, the same sequence AI. And in the second version, we cannot. Okay, first things first, we have a sequence. AI1, AI2, AI3, etc., AILI. What can possibly be the max after adding some integer x? I claim that there are two versions. So it can be max of AI. So it is equal to this number, which we will call, okay, let's call it B of AI. It can be equal to this number if x is not equal to BAI. And also it can be equal to C of AI, which is max of AI with BAI. If x is equal to BAI. It can be called first max and second max. So this is the first max, the minimum number which is not in this sequence. And this is the second minimum number which is not in this sequence. And after the operation, we either get the first max or the second max. We cannot get anything greater than it or anything other than it. So basically, each sequence can just be replaced with two numbers, B and C. And x is transformed to B if x is not equal to B. And x is transformed to C if x is equal to B. So we have several pairs of numbers. And we have these transforms as I wrote to the left. We want to maximize our number. In the easier version, we can run the same transform twice. In the second version, we can. Let's solve the easier version where we can use the same transform twice. The key ingredient is the number m0. m0 is just f of 0. Or even f of minus 1, I don't know. Okay, f of number x which is not present here. F of minus infinity. Okay, m0 minus infinity. So I claim in this problem that all numbers from 0 to m0 go to simply m0, and all numbers which are greater of m0 they just go to themselves. So we cannot increase a number which is already greater than m0. Okay, how to prove it. Well, basically, I can just prove that M0 here, so here M0 is just the maximum of all B's and C's. So M0 is the maximum of this table. And since BI is always less than CI, then it's just the maximum of all C's. So M0 is the maximum of all CIs. Okay, let's assume firstly that the number is greater than the maximum of CIs. Then I claim that we cannot increase it. It's obvious because any operation will make our number equal to some BI or to some CI, which is worse than to not touch it and let it be I. Okay, the second case is number I is less than M0. Then I claim that we can make it exactly M0. For example, it is C3. So if our number is equal to B3, then we just run this operation and it becomes equal to C3. If it is not equal to B3, then we run 2 times this operation. After the first time it becomes B3, and after the second time it becomes C3. Okay, so in 2 operations, or in 1 operation, if it was less than M0, we can make it exactly M0. Therefore, we want to find this sum of from I from 0 to M, maximum of I and M0. This is what we want. This is very easy to calculate because, well, there are 2 cases. That this maximum is equal to M0 and it is not equal to M0. Okay, so let's decompose this into 2 sums. From 0 to minimum of M and M0. And in this case, this maximum is M0. Plus sum from this minimum plus 1 to M. And in this case, it is I. Okay, this sum is easy to calculate because it is M0 times minimum of M and M0 plus 1. This sum is also easy to calculate because we add the minimum number of the sum, which is minimum. Okay, let's call this minimum like N0. So N0 plus 1. Then we add the last number. Then we multiply by the number of numbers, which is M minus N0, and divide by 2. So this is the answer. M0 is the maximum of all C's. This concludes the part A, the easier problem. Now let's solve the harder problem. In the harder problem, we can only invoke each operation once. Okay. Again, we have some B's. And C's. If our number is not equal to some B, then the operation makes it equal to this B. But if it is already B, then it is equal to C. The key difference is that we cannot make any number automatically equal to any C, because we would need to apply the operation twice, and we cannot do it. We can only make an operation once. Good. Let's then draw a graph. So we have some numbers, like, and let's draw an arrow from some number to other number, which is called arrow number I. If this number is equal to BI, and this number is equal to CI. Then we connect them with an arrow. if there are several operations with the same b's, for example, or with the same b's and c's even, then we draw several arrows corresponding. Okay. Again, let's say that m0 is f of minus infinity. So the maximum number that we can get if we start with the number which is extremely small. Okay, how to find m0? Well, actually, to do that, firstly, we want to find some other function g. Let me think. No, it's fine. Okay, so firstly, I want to find this function f for all these numbers. Okay, no, sorry. Let me reformulate this. No, I need function g. So g of x is the maximum number that can be achieved, reached from x only by operations of form BICI. Yeah? So, okay. Let me reformulate. Let me remind you that when we call this function number I, yeah, so x under the operation number I is either BI if x is not equal to BI, or CI if x is equal to BI. Let's call this first type, and this is called the second type. Yeah, so we can call operations of first type and operations of second type. So here I say that I only allow the operations of second type. The first type is not allowed. So g of x is the maximum number that can be reached from x if you only run this case. So if number is not equal to bi, then you cannot run ith operation. Okay? So most probably g of x will be equal to x. Yeah, because most probably number x is not equal to any of these, so it has to be preserved. However, if x is a number among these ones, then we can do something. What can we do? We can run among these edges. Also note that since each bi is less than ci, there are no cycles in this graph, in this directed graph. So we can like always use the edge. If we use some edge, there is no problem with the fact that we cannot invoke the same operation twice. Because the second time we just cannot appear in this vertex. Because we only increase our number by the second type operation. Yeah, therefore, g of x is the maximum number reachable in this digraph by edges. Okay? How to find it? Basically, let's sort all b's and go through them in decreasing order. So what is g of bn? G of bn is obviously cn. Okay? Well, not. It's not true because, for example, if there are two edges from bn, which is 6, 7, and 6, 9, then 9 is the answer, not 7. So, like, bn is the maximum among all edges from Bn to something of this something. For each of the other edges, we can find it recursively. For example, what is g of like bt? G of bt is the maximum among all edges where bt goes to some cs of g of cs. Or bt if no edge starts at bt. Well, it's impossible, yeah, because since I called it bt, it's a b for some c. So therefore, there is definitely some edge. So this comment is only for x's. So g of x is x if x is not equal to bt for any t. Okay? So first thing that we do is we calculate this g for all these b's. I would say that it can be done with DFS, but actually no DFS is even needed. You just iterate over them in the decreasing order. And for each vertex, you just find the maximum of g's of the ends of the edges. This can be done like with unordered map. So for each number, you store the set of all endpoints of these edges, and then you iterate over them and take the maximum. Okay, now we are able to find this function g. What about m0? Yeah, so what about m0? m0. Obviously, in m0, you will have to use first type operation. Why? Because if you don't use any first type operation, then you lost. Then you definitely lost, because you just cannot use any type of operation and you're left with minus infinity. So you have to run at least one first type operation. So m0 is definitely at least maximum of all BIs. Well, what if we want to run some... Let's take the last first type operation. So this is the last first type operation. So probably we then ran some second type operations. But how could we? Yeah, so bt is the beginning of some edge number t. If we then want to run the second type operation, then we want to run the same edge t, which is impossible. We can't run 2 times the second edge, the same edge, bt, and then ct with the same edge t. It's forbidden in this hard problem. Well, actually, sometimes you can, if bt is the beginning of several edges. If there are several edges starting with bt, then you can run the first type operation with some other edge and get x equals bt. And then the second type operation with this edge and go here. Okay? So what do I want to say? I want to say that not only at least maximum of BIs, but also maximum of all g of x's, where x is at least twice a beginning of an edge. Notice that it can be proved the other way. So I proved that if the number can be reached, then it is at most this number or this. So, okay, I claim that m0 equals f of minus infinity equals maximum of these two maxima. First of all, maximum of bi and maximum of g of x, where x starts at least two edges. Let's prove this. First of all, let's prove that m0 is at least these two numbers. Why is it at least this number? Because we simply can run one time the first type operation. Why is it at least this number? Because we can run the first type operation with this x. Yeah, for example, we need this path in our G. And this vertex is the beginning of two different edges. So let's run the first type operation with this edge, and then the second type operations with these edges. We can reach it. Okay, now let's prove this thing. To prove this thing, we need to consider two cases. Either we had at least one second type operation, or we did not. If we didn't have any second type operations, this is obviously this thing. If we had second type operation, let's consider the last first type operation. It is in some edge. Sorry. Sorry, I didn't mean that. I mean, first case is last operation is first type, and second case is last operation is second type. Okay, in this case, this is obviously at most maximum of bi. And in this case, we have some first type operation and then several second type operations. Okay, so I claim that this vertex is the beginning of two different edges, because there is an edge along which we made the first type operation, and this along which we made the second type operation. So this is the beginning of two different edges. So I claim that it is at most g of x for this x, just because the maximum number that can be reached from here by edges is g of x, and we reached it by edges. Okay, we have proved it. Can we calculate m0? Yes, we can. Because this is simply can be done in a linear time, and this can also be done in a linear time because we have pre-calculated all g of x's for all x equal to some bi. So now we know m0. Moreover, I claim that m0 is maximum you can get from any number. If you must run at least one first type operation. Because at the moment you make the first type operation, it does not matter what you did before that. It doesn't matter of what is your number m0. Well, I kind of say that we are allowed to run first type operation even if we need to run the second one. Yeah, so for example, let's assume that we have b1 and c1, and we have x equals b1. I claim that you can. So in our problem, you cannot run first type operation. You have to run the second type operation. But I say let's allow to run the first type operation in this situation, because it doesn't help you at all. So it's allowed to first type here. It doesn't help us because it doesn't change the number at all. So if we make this amendment, then M0 is also maximum you can get from any number if you must run at least one first type operation. Because the moment you do it, you just ignore whatever was before that, and before that you can assume that your number was minus infinity. And since it was minus infinity, then it's just now equal to M0 by definition. Okay, good. So we have calculated M0, we have calculated all g of x's. Now we need to calculate all f of x's. Okay, how to do that? What is f of x? It is maximum of several things. It is maximum of M0 and g of x. Yeah? Because if we don't run first type operation, it is g of x. If we run first type operation, it is M0. Okay? So how do we calculate sum of all numbers from 0 to m, f of I? Okay, how to do that? Let's write it f prime of x equals maximum of m0 and x. Then this is equal to sum from I equals 0 to m, f prime of x plus f of x minus, oh sorry, x is here, minus f prime of x. Okay? This is calculated, let's divide it into two sums. So f prime of x and plus the second sum, which is f of x minus f prime of x. So this can be calculated the same way as in the previous problem, because it's just maximum of a constant and x, and it's like sum of arithmetic progression plus sum of constant. So this is easy. Now let's calculate this thing. What is this thing? So notice that if g of x equals x, this is equivalent to x being some bi. And if g of x is equal to x, not being equal to some bi, and if g of x is equal to x, then f prime of x is equal to f of x. Yeah, simply because this equals this. This means that these and these maxima are equal by definition. By definition. Right? So actually here we can only consider sum of x's that are from 0 to m and that are equal to some bi. Okay, so there are linear time of this axis for which this can be different. What can we do in these cases? In these cases, we just need to calculate f prime of x, which is very easy. We need to calculate f of x, which is really easy because this is constant and this is pre-calculated. Subtract them and add to the answer. Sometimes it will be 0, sometimes it will be not 0. Well, that's it. So the key observation is that while this sum contains 10 to the 9 plus 1 addends, because m can be really big, we're only interested in these numbers, which are both from 0 to m and which are met among bi's. And there are not many of them. So for them, we can manually recalculate this addend. Okay, that's it. Thank you for watching. Is the system testing over? Yeah, it's over. Now let's submit problem F. I think it will be wrong answer or time limit, but who knows? Are you serious? Ah. It actually just worked, doesn't it? It works. Okay, time limit. Well, still it's possible that this solution is working on C++20, but I don't think so actually. Compilation error? Ah, contains. We cannot use contains, really? Okay, I remember. We cannot use contains, of course. We can always replace contains with count. What now? Ah, no such file directory optional. Oh my god. Okay, I can remove optional if you don't like it. What again? I removed contains, didn't I? Ah, C++14 also doesn't know about this. Sad. Do we have any other C++s? No Visual C++? Okay. Okay, everything is too slow. Therefore, I won't explain this problem to you because I don't know how to solve it. Thank you for watching.